Our next speaker is Deepak Dhar. He's talking about entropy of hard straight tremors on the kagome lattice of full packing.
Okay, so let me start by thanking the organizers for giving me this opportunity. This work is done with several people: Jürgen Stilk at UFF, Brazil; Tiago Oliveira at Vicosa, Brazil; Abhishek Dhar, and Rajesh Ravindran. So the definition of the model: trimers are straight rigid rods of width 1 and they occupy 3 sides on a lattice. The lattice is this kagome lattice. It's called the Japanese basket pattern. Not particularly Japanese, but the name is Japanese. No interactions except hardcore interactions between these rods. And so you just ask what will happen if you put all these hardcore particles on a lattice. We will study the special case when all the sites are covered. Okay. So this work is sort of based on a lot of earlier work. The problem of statistical mechanics of hard rigid rods has a long history. Needles of length k are called kamers. The starting work is Onsager, 1949. He showed that long rods in 3D solution become nematic at high density. And that was the first example of a geometrical phase transition. Swansea studied this same model, but on a lattice. On a lattice, the main difference from the continuum model of Onsager is that the orientation of rods are finite and they cannot be changed continuously. And the particular case k equal to 2 has been studied a lot. This is called the dimer model, starting with the famous solutions of Castellin, Fisher, Hughes, and so on. For k equal to 2, it is known that there is no phase transition for any density rho less than 1. And a full packing case is exactly soluble k equal to 2. No exact solution for other k for other regular lattices. So for k equal to 3, even on the cubic lattice, there is no exact solution so far. But we found that for kagome lattice, one can find one. So on a square lattice, there is no phase transition for k less than 6, but 2 phase transitions for k bigger than 6. So at low density, you have a phase in which the horizontal and vertical rods are equally likely. Then at intermediate densities, one of the two becomes preferred. And at very high density, again, they become equally likely. So there are 2 phase transitions. And some asymptotic results are available for large k. If k is very large, long rods, there is the kind of stuff which Onsager studied long ago. From nematic to disordered, the second transition, it turns out to be first order transition where there is a jump in density as a function of activity. And some results about the position of the jump and the size of discontinuity, etc., can be studied. So then, since not too many other solutions on regular lattices are possible, we studied the case of Bethe lattice, which can be solved for general k. And then Rodriguez et al. Studied the case of these Huisimi graphs, which are like Bethe lattice, but they have triangles. And then since they were triangles, we thought that this will be similar to the kagome lattice. And so we said that maybe this is similar to the, the answers are close to the kagome lattice. So how good is the approximation for the kagome lattice? So we studied the kagome lattice in that case. And interestingly, some unexpected features emerge, which is that it becomes actually exactly soluble. And so that is what I'll try to discuss. So trimers on the kagome lattice at full packing. So the kagome lattice is drawn like this for convenience because some of the axes are now rectangular. It is convenient to do it in simulations, and it is just a coordinate system. And at maximum packing is 1. You can actually cover all the sides, and this figure shows the arrangement. Of course, you can take some other directions in which this can be done. And then what happens if you make the density a little bit less? Then you can remove some rod, and then maybe one can slide the other rods into that position. But these changes are very local. And so this long-range order, periodic order, seems to be surviving small number of defects. And so we were expecting that this system will have a layering at high density, and it will show a phase transition from disordered to layered structure. So from the fully layered state, one can try to develop a perturbation expansion in powers of density, which we tried to do, and first few terms looked well behaved. And so we were expecting a first transition. However, we looked for this phase transition using Monte Carlo simulations, very efficient strip algorithm. So Rajesh could not find any clear transition. In fact, he could relax very quickly for high reactivity. And then we generated a configuration like this. So where these are not local defects, but there is a string of lines. And this is a fully packed configuration with 2 defect lines which goes and wraps around the torus. But of course, if there are 2 defect lines, then this stuff has much more entropy than the fully ordered state. And so this will swamp the periodic state. And so it will have no order. So such disordered configuration must dominate at full packing limit. And in fact, the number of distinct full cover configurations goes exponentially with n, for large n. And so the entropy is bigger than log 2 by 9 per site. And so this is a proof. So you take the kagome lattice, think of it as a sum of pink triangles. Each site is part of one triangle, and each triangle can be covered in 2 ways. 3 rods like this or in the other way. And so each, so the total entropy is bigger like this. While this lattice does not have sliding instability, it can produce extended defect lines, and this is shown a picture of an extended defect line. The position of the boundary between 2 differently layered phases. So here this is, green and vertical, but they are shifted with respect to each other on the left and right, and there is the boundary. And the boundary can just move one step, either stay at the same place or move one step to the left. And the boundaries can come close, they do not annihilate, but eventually reflect. If you have 2m boundaries, then the problem becomes that of free fermions with a single particle spectrum like this. And then in the large n limit, you can show that the number of defect lines grows as 2l by 3, and finally you get an entropy like this. These results have been verified by explicit sizes. L, this is the entropy per site, and these are the sizes, and this is for k equal to 3, k equal to 4. And finally, this calculation can be easily extended to cases having 3 different activities, Z1, Z2, Z3 for 3 orientations. Matrix problem is exactly the same as that on a hexagonal dimer model, but this equivalence has some holes in the proof which we are trying to fill. And we are also studying cases for higher values of K4 and 5 on the same lattice. So let me stop here.
For the nice question.
Yes. Yeah. So, yeah, so if you have 2 defects, they cannot come close to each other, but one can check that actually it can be solved by Bethe ansatz, but that Bethe ansatz is very simple. A Slater determinant solution actually works for 2k defects moving. By explicit solution of the transfer matrix, you can check that the free fermion wave function is an exact eigenfunction. Yeah, there is no parameter. As I said, you can introduce parameters. These are the 3 activities, Z1, Z2, Z3. Interestingly, the answer is the same as dimer coverings with 3 activities, Z1, Z2, Z3. Correlation functions we have not yet managed to calculate.
But strong, you are able to calculate the correlation function, it will be the topological function, not the conventional.
Right now, there is no phase transition here. It has the same phase throughout.
I saw that you see the transparency that the Robi German has not able to find in transition.
Yeah, yeah. No, you can have more lines. Sorry. This one has 2 lines. You can have 4, 6, 8, depending on the size of the lattice. And so the number of lines is proportional to the width of the lattice in the most likely state. We are working with the periodic boundary conditions. Otherwise, you have to have specify the boundaries fully, and that's extra complication. The number of lines is even because there are these phases A, B, A, B, A, B, and so the number of lines, the boundaries has to be an even number.
You talked about nematic phases, so these can be considered as a high density state where their domains are separated by defect lines.
Yeah.
And similar thing can be seen for liquid crystalline.
Yeah. So here you can say these are layered phases because there is a horizontal layering in this case. But actually it turns out that in the most likely state, the 1/3 of the particles are in orientation 1 and 2 and 3. So all the orientations are equally likely and there is no layering. Other way of saying this is that you can also say these are the layers are like this. And it turns out that all the directions are equally likely in the end.
I have run some simulations with liquid crystals in 2D. And I have exactly similar pictures I will show you.
Okay, very good. That will be very nice.
Basically, very similar question. You answered it already. But yeah, this looks like some different kind of liquid crystalline phase. It's not really symmetric.
Yeah.
But it's like chaotic. I don't know how to describe it.
So if you take the Z1, Z2, Z3 model where Z3 is less likely, then you actually get layering. But with Z1 equal to Z2 equal to Z3, we actually don't have any ordering and it is a disordered phase, just like the dimer model in 2D is disordered.
Can we expect some topological defects, just like we observed?
If you make defects, of course, they will be there.
This dictated by the underlying lattice.
Yeah.
I mean, defect lines might be coming due to different origins, but topological defects which are singularity.
So we were studying the full packing case where there are no such defects. If you have defects, typically what can happen is that you can generate, these lines never stop and end. But if you have defects, you can actually generate 2 lines from nothing, which will go and later on rejoin at some other place. At the place where they start or rejoin, there is some defect density and there is some loss of, there are some empty spaces. And so that's the defect. A defect can be the source of these defect lines.
Further discussions we can have at the tea time. So thanks you once again.
Thank you.